So in this section of experiment, there is the standing wave measurements, that we have to learn how to measure the SWRs using slotted line and SWR indicator. Okay. Uh, at any point of along a transmission line, we can think of the electromagnetic field as a sum of two waveforms. One is traveling toward the load, and the other is traveling toward the generator. The reason for the reflection is, as was already discussed in the previous chapter, due to the impedance mismatch. Okay, any open spot on the line is considered to be an impedance mismatch and becomes a cause of the reflection as well. The amplitude and the phase of the reflected wave depend upon the load impedance. The degree of the attenuation of the line affects the amplitude of the reflected wave also. The only way the reflection can be eliminated is either the line is infinitely long or there is impedance match between the load and the transmission line. So that is the standing wave patterns in a lossless line. Short circuit, all are adjusted with each other. Open circuit, there is a shift between these two. Resistive capacitance load, it will be a simple part, but uplifted and resistive inductive load, that has been, as you can see, 90-degree shift. So that is the basic formula of SWR. Okay, if you know the VSWR, it's Emax divided by Emin, and then you can write it like that: S minus 1 divided by S plus 1. Rho is here for the reflection coefficient, so that will be equal to S minus 1 divided by S plus 1 under the reflection coefficient. So now go through to the setup equipment. That is the setup equipment on that particular portion, that is quite similar to the previous sections, that it should have to be a power supply, to the gun oscillator, the square wave generator, to the PIN diode modulator, that's the modulation section, that is the input section of the waveguides, and there is a variable attenuator there, and the variable attenuator has been set to 10 decibel, and there is a slotted line, and in that part of slotted line, that is the SW indicator has been connected, and the slide screw tuner to tune the slotted line, and match termination to match it and get the Z0 matched with that. Now in the second in the seventh experiment, that is the impedance measurement. We have to learn the Smith chart and its application in determining unknown impedances. That is the reflected signal, that is the reflection coefficient. Okay, equation, that's the very own theory that we have learned in the previous theory parts. So that is the VSWR, as you can see here, and we have to obtain the data waveguide through well defined measurements, determine the magnitude of the phase of the deflection coefficient, and calculate the load impedance. The Smith chart is used for the third process of determining the load impedance. Okay, now it is quite known to us, that is the maths has been done by this, and you know that how to measure the SWR, and there is a simple video on my YouTube that I have posted, how you could measure the what can I say, the SWR and the matched load, okay, by Smith chart. So solving example through this, and there's a pretty much a math type, and just there's the setup diagram, same as before, that we have taking the impedance measurement in the previous experiment. That is the same with the experiment number 6 setup and experiment number 5 setup, and get the impedance measurement, and just compare it with the calculation with Smith charts. And that is the 8th experiment. There is the basic properties of a directional coupler. The objective of the basic properties of a directional coupler including coupling coefficient and the directivity. That is the directional coupler. As I always say, the collinear arm is the parallel arm is known as the main arm of a directional coupler, and there is an auxiliary arm. So it's basically a sampling device of microwave signal. The importance of the directional coupler is as a sampling device is that it does not introduce reflections to the main system. The physical structure of directional coupler can be thought of a transmission line with one input port but two output ports. Okay, just you can imagine that it's one kind of a waveguide. It's a one input port and two output ports in the both sided directional coupler that has been given here. So the directivity of the directional coupler allows the energy coupling in the one direction only. That is the directivity. The directivity shows that how much power go through to the main arm. Okay, it's the directivity measurement of directional coupler. Okay, and the basic properties of directional coupler is graphically presented. Okay, that's the directional coupler contains a matched termination. So that is the basic properties, and some power go through to that. The coupling coefficient means the third port is the coupling port. So how much power has been coupled, you can find out by this equation 8.1. And directivity means how much directed the power that go through to the, as you can say that how much directive the power that go through to the waveguide. Okay. Now that is the return loss measurement. To find out the return loss, we can use the device under test DUT, and the input signal is applied at port 2 to find out that, and that is the coupling coefficient, that is C, that is P3 is equal to PR divided by C. So that is the SWR calculation through to the reflection coefficient, and the experimental procedure is the coupling factor measurement. We have to set the variable attenuator to 20 decibel and apply 1000 pps modulation signal to the PIN diode modulator, turn on the GAN oscillator, then read the SWR inductor, the value as a reference, and fill the table. Okay, that is the basic initial setup for coupling factor. It is simple as you can say. That is the input part. That's the input part through the variable attenuator. After going through the waveguide, check the SW inductor with the crystal detector, and just fill up the value through that. Replace the frequency meter with the directional coupler and move the crystal detector auxiliary arm and find out the power through that. Adjust the variable attenuator until the same reference reading as obtained. Fill the table 8.1 attenuation of the attenuator. The coupling factor in the directional coupler is A1 minus A2. So setup diagram for coupling factor measurement, that is the setup diagram, and with the directional coupler. With the directional coupler, the main arm has been connected to the matched termination and the input section of microwave setup, as you can see, microwave measurement setup, and the another arm, one arm is the main arm, the coupled arm has been connected to the crystal detector and HW indicator. So directivity measurement, if you want to calculate if you want to measure the coupling factor, okay, through the directional coupler, the auxiliary arm should have to be connected through the SWR indicator. And if you want to find out directivity, the connection should have to be altered, okay, just altered to the with respect to the auxiliary arm. Okay, then you can find out the directivity out of it. Okay, and if you want to find out the return loss, So that is the setup for the return.